Hi, my name is Andy Kong. Today, on behalf of my co-authors Chris and Dewa, I'd like to present our work, Power over Skin. Advances in electronics have enabled small yet powerful wearables for health and entertainment applications. But despite these advances, batteries haven't evolved nearly as quickly, and they still contribute a lot of the bulk and the weight in these wearables. The effects of this are twofold. One is that existing devices are kind of big. Like this ring, I think, is kind of chunky compared to a normal ring, since they have to carry all their power with them. And secondly, it precludes certain wearable form factors, such as health sensing patches or jewelry. These don't really exist commercially because of the difficulty of incorporating a battery. So let's cancel batteries. What can we do instead to power these wearables? So one idea is you already carry around devices with batteries, such as your phone or your smartwatch. How can they share this power with little devices? And this isn't such a pipe dream, right? The older generation should recognize that wired headphones are an example of passive devices that share power from our larger devices. But if you have multiple devices, wires are pretty unfeasible. What's the alternative? How else can we do this? So we draw inspiration from the field of body area networks. So these find that high-frequency electrical signals can pass through the body pretty easily. They use this to transmit data between a transmitter and a receiver. But why not turn it up a notch? Let's also send power. We've envisioned a future where you can incorporate an RF transmitter in an existing device like a phone. This couples RF energy into the body and powers a network of battery-free wearable devices for all sorts of applications. So a bit of background on this technique. We're not the first to think of it. These are the existing papers in the field. And they're all pretty similar. They use the skin as a wire to pass RF energy between a battery-powered transmitter and battery-free receiver devices. But they also have an issue. Wearables need certain traits from their power source, right? They need high enough power to do sensing and communication. They need this power to be accessible at different parts of the body. And they need to be small, or else you would just use a battery instead. But the existing approaches only let you pick two of these features that are critical in wearable devices. In light of this, I'd like to introduce our work, Power over Skin, full-body wearables powered by intra-body RF energy. We achieve a very small receiver size, which is capable of harvesting enough power over the skin to run a microcontroller and sensors. And we can reach this power across most of the body. So how does this work? The skin is slightly conductive, and especially so at higher frequencies. If you look at the skin transmission efficiency graph, you'll see a peak around 40 megahertz. This means that if you're touching a transmitter that's going at 40 megahertz, it will fill the body pretty evenly. You can see from this guy, he's fully red. Then it's just a matter of harvesting this power. For the details of how we implemented it, I'm going to walk you through the same way the power path goes, from the transmitter to the skin into the receiver. So we'll start with the transmitter. The fundamental question is, what kind of waveform do you use for transmitting power? And sure, the graph just says 40 megahertz. You can make a sine wave and just couple it right into the body. But if you look at the graph closely, there's actually a range of frequencies which work, right? Anywhere from like 40 to about 100 megahertz. And just because the gain is lower doesn't mean that you can't transfer any power. And so part of our paper is we propose using a different waveform, such as square waves, which are able to send multiple harmonics of this fundamental frequency, allowing you to send multiple signals at the same time. And you can get more out of this curve than you would with just a sine wave. For instance, in our testing, we found that square waves actually transmit 75% more power than sine waves for the same peak-to-peak voltage. But that's not the only cool part of using square waves. You can also generate them really easily using a microcontroller. Because they all have a clock signal, you can just ask them to output this clock on one of the pins, and boom, you have a square wave, put it through an amplifier, and you can just couple it into the person. So that decides our transmitter waveform, 40 megahertz square wave. But there's another issue once you get to the skin interface. So higher energy RF actually doesn't really like going into the body. Some of it will bounce because your impedances aren't matched between the skin and your amplifier. So one thing you can do is you can make an LC circuit which impedance matches the amplifier in your body, and then it allows you to preserve your transmission efficiency. So once the energy enters the body, what happens on the receive side? So all the receivers that you're wearing will see a very attenuated waveform. This is because the body actually doesn't really like transmitting power. You're kind of making it do it. And this is an issue for us because when you actually rectify an AC signal, you have to use a diode, and this incurs a voltage drop. If you already have a very small voltage, you incur a voltage drop, you end up with almost no power. So one thing you can do on the receive side, which is really clever, this was proposed by Lee et al. In Nature. You can use an LC circuit which is matched to your transmitter waveform, and it passively boosts the voltage of your transmitted signal on the receive side. And this is without using any power. It comes at a cost of the reduced current, but it allows you to get more power out of the skin. So after this, it's pretty simple. We rectify it into a DC voltage and then store it in our capacitor. And once you have the power on the receiver, you can use it for anything. We do communications, we do Bluetooth, we run sensors, we do computation, we take input, we run a display. But I'm not going to leave it all for you guys to figure out. We made some demo apps to show you what we can do with this thing. So our initial prototype was a blinking LED, very simple, just to show that we had power. And we used this to debug how much power we were getting, and this is blinking entirely off of power harvested from body contact. We later repurposed this into a light-up earring, and here you can see it. So the ground plane is decorative here. It's used as like a little snowflake pattern, and the power comes in through the ear contact. But this is just an LED, you know, like what else can we do? So for a more complete example, we took this calculator and just butchered it. We took all the power sources out of it, we removed the solar panel, and then we put our receiver in. This is the only power source on this calculator. And you'll see I'm wearing a transmitter on my left arm, which is out of frame, but as soon as I touch the calculator, you'll see that it powers on. And this is because it's harvesting the energy through my body contact. And this demonstrates input, output, and computation in this commercially available device. But let's do some more connected stuff. So we were also able to incorporate this into a ring controller. So this is a 32 megahertz microcontroller, full Bluetooth stack, and it has a joystick. And so it allows the user to send in real time commands to their devices, and it's powered entirely over the skin. So here's a video of it working on a TV. We envision that not only can you control a TV, but you can incorporate this transmitter into something like a VR headset, and you can have the headset power its own controllers just over the skin, and then you don't need to charge two devices. For lower energy applications, we also made a really slow Bluetooth thing. So this is a thermometer, and it measures someone's core temperature. It's a little patch thing, and it sends this data to a laptop or a phone every 5 minutes or so. I almost always have one of these demos on me, so if you want to see it in action, just come find me. And I'll also be at demo night tonight, so I'll be around. So once we decided the implementation of our thing, we wanted to test what conditions does this really work in, how much power can we expect out of this thing. So here's some of our evaluation experiments. We actually tested a lot of things, so you should check out our paper for more details. I couldn't fit it all in here. So the first question is, how much power can you actually get? I said 40 megahertz goes well, and then I said it attenuates. What are we looking at? So prior work stated that power falls exponentially with on-skin distance. Exponentially fall off is pretty bad for power, and we found this also to be the case when we tested it on the arm. But weirdly, we saw you could still transmit power from arm to arm. You could get it from one side of the body to the other. So it wasn't exactly linear with on-body distance. And since it was such a complex thing, we ran an empirical study with a bunch of people, to figure out, depending on where you put the transmitter, how much power can you get at each receive location. So we picked a couple of transmitter locations that we expect you to already have devices that have batteries, or that won't mind the weight of adding a battery. For instance, the head is where a headset might go, the wrist for your smartwatch, the pocket for your phone, on the waist and in your shoe. So these are our transmitter locations. And then we found some receiver locations that would be nice, are difficult to fit a battery due to size constraints, or that they're just well spread out on the neck, the hand, and the chest. And then we crossed them. Every transmitter and every receiver were tested separately, and we measured how much power is available, and we generated these nice heat maps. So this allows us to figure out, if we put the transmitter on the wrist, how much power can we expect on the arm, and this sort of thing. The thing I want to draw your attention to is the right figure. So this is the left pocket transmitter. And what's neat about this is that it's almost the same color as all the other heat maps, which means that the power transfer is about the same. You see that they share a scale. This is neat because this transmitter isn't even touching you. This transmitter we actually just put in the participant's pocket, and it couples through clothing, which is pretty neat because it allows you to be more loose with how you implement this into existing devices. So pretty cool. Another thing we wanted to test was, since the effect is capacitive, do you really need electrodes? All the prior work that we could find used either metallic electrodes or wet electrodes. That's not super nice. And so we're curious if it would work with any conductive stuff. We got everything conductive I could find in the lab, which is a smattering of different materials. Here's copper on the right. This is received power using a copper electrode versus all the other ones. You see that a lot of them transfer power just as well. And many of these are fabrics and rubbers, which is pretty neat because it means that you don't need to have exposed contact like this for it to work. And the last question is, does it scale? We made a ton of devices, and we say we envision a network of receivers. Does it actually work on a bunch of them? So what we did was we got someone's hand, and we got a bunch of receivers, and we added one at a time and then measured how much power is available on the limb. And here's what we find. So there's a bit of a linear fall off. This is just measured on one receiver. So actually what you find is that they do share a power pool, so there's a bit of a fall off and interference pattern between each of them. But it falls off pretty slowly, and it's not zero sum, right? The power is shared, and in total more power is transferred because each of these gets to access the same amount of power. And this test is also a bit against our favor since they're all on the same limb. Normally you would have them shared just across the whole body, and then hopefully they would interfere less. So, it's not perfect. I really like this project, but there's some drawbacks. I think the main drawback is we actually don't get massive amounts of power. We have a reasonable amount of power, which is better than nothing, but only compared to prior approaches. So here's some typical devices that you might have seen before. The earbud is the only wearable here, all in the low watts or high milliwatts. Here they are on a log powered chart, and here I add power over skin. So you see it's about an order of magnitude lower than earbuds. But I argue that this actually is pretty competitive because there are existing devices that you may already be wearing, such as a glucose monitor or a fitness tracker, which use much less than this amount of power. And we're able to get this entirely over the skin, and we're fighting against devices that have batteries in them. So I think it's a pretty usable amount of power still. Another issue is that the body proximity affects delivered power. So you see here the chest is a bit lower than the left arm, even though it's closer to the transmitter. What's up with that? Since the effect is capacitive, if the same signal couples into both the body electrode and the ground electrode, then you reduce how much power you get after you harvest it. This is a problem because it means you have to design the ground plane so that it sort of hangs away from the body. For instance, this earring is perfect because the earring is always hanging. But in certain other applications, it might be harder to find a place to put it. And the last question I want to answer is this safe? Every time I tell people about this, they're like, like, is this good, right? So I pretty extensively read the guidelines for this, and the only problem comes from heating. So as this passes through you, it attenuates a little bit. Your body picks up that heat, right? At our frequency, it's recommended for an average person to have the total power be under 5 watts. Our transmitter, even our benchtop transmitter, cannot get within 10% of that. So at least in our implementation, this is entirely safe. So I'd like to conclude now. We advanced the state of the art in how much power and how far you could transfer intra-body power using several RF optimizations, which are detailed in the paper. We then conducted a bunch of experiments, some of them being materials testing or power budget at different locations to characterize our implementation for reproduction, and also made several demo apps showcasing potential use cases for this. We look forward to the future of wearable battery-free devices, and now I'd be happy to take any questions.
Thank you, Andy.
So yeah, it's a great presentation, and personally, I'm also doing something about electrotactile. It's also releasing power to the skin. So I wonder, you gave us a lot of parameter about the power, but how about the voltage? Because I knew like the voltage above like 100 volts or 200 volts, you can feel this, like if you pass through your surface skin. So whether like, can you give me more?
Sure. What kind of frequencies are you working with?
Like I'm working with DC converter,
Oh,
like
I
DC.
see. So at high frequency RF, your body, like the water is too slow reacting, so you actually don't feel anything. It effectively is charge neutral. At 40 megahertz especially, like no one has ever reported anything, and it's too high of a frequency to really be felt as like individual stimulation. So even though the voltage is like, we've used like 20 volts in the past, it's sort of more characterized in how much power you can transfer.
Oh, I see. Thank you.